Good afternoon, everyone. So we'll be presenting our work, Multi-Accent Neural TTS for Low-Resource Indian Languages. So here are the contents of our presentation: introduction, methodology, dataset, TTS model details, evaluation techniques, sample outputs, conclusion, and references. So the main objective of this work was to develop a robust multilingual voice cloning TTS model for 11 Indian languages, to bridge the gap for low resource languages, and to build a lightweight, efficient TTS models that supports voice cloning, and it's compact in size in MBs for deployment on real-time applications. So this is our overall methodology. The multilingual speech text dataset provided to us were the SISPIN and Spire dataset. Along with that, we included INDIC TTS and INDIC voices corpus. And so there were total 11 languages and 35 domains. Out of that, we sampled and filtered few of the domains in round 1 and round 2, and then used the IMS token TTS base model and fine-tuned that model based on the sample dataset, and then perform the speech quality evaluation. So first of all, we'll come to the dataset distribution. You can first set of the columns represent the SISPIN Spire dataset, and the second one are INDIC voices and INDIC TTS. So considering that this is meant for healthcare domain, we selected out of the 35 domains present in SISPIN and Spire, we selected food, health, agriculture, and regular conversations, and formed the sampled set of corpus. And in order, also SISPIN and Spire has only one male and one female speaker. So we also included multiple speakers from INDIC voices and INDIC TTS for the languages which they support. And we formed the total corpus of 621 hours for all the 11 languages. The overview of the architecture. So we have a reference audio, a language ID, and the text. The text is converted to phonemes, and then from the phonemes, we extract articulatory features of 64 dimensions. And from the reference audio, we extract the speaker embeddings. And from the language embeddings, we concatenate all three of them, pass it through the encoder network. And the encoder network is next passed through a variance adapter, which actually predicts the pitch, energy, and duration of the phonemes, which is then converted to a MEL spectrogram using the decoder network. And the MEL spectrogram gets converted to speech using hi-fi and vocoder. So the first step of the model was the data preparation. So in the data preparation, first thing was to convert the text and normalize the text. So if we can have digits, we can have code mix text. So we use eSpeak NG phonemizer for converting the entire text into phonemes. Now there are 4 languages which are not supported in the eSpeak NG phonemizer. For that, what we do is we convert the numbers into num2 words, and then convert that into the script of Devanagari, and then pass it through transphone. Transphone supports the other 4 languages, and then ultimately the entire text is converted to phonemes. So those phonemes after that are pre-processed to get the 64 dimension articulatory features. So these articulatory features signify if they are voiced or unvoiced, if it's a vowel or a consonant, the position of the tongue, it's a labial or a dental voice. So all of this are represented in form of a 0-1 binary format of dimension 64. And next we have the audio files, which are now converted to MEL spectrogram. And we also have an aligner, which will give us the timestamps of each phoneme and the duration of that phoneme in the entire, of all the audios in the corpus. So, and also we have the speaker embeddings using the eKappa TDNN model. So these are all our pre-processing steps. So ultimately we have a speaker embedding, we have language embedding, we have the phonemes and their articulatory features, and also ground truth, pitch, energy, and duration. So for training the model, once the text is converted to the phonemes, we are passing those hidden representation to variance adapter, which can convert the phonemes or the representation into frames of each frame, and then those frames will correspond to a particular pitch energy, and then with the help of a length regulator, we will decide how many frames correspond to how many phonemes in the speech, and then convert that into a preliminary spectrogram or the MEL spectrogram. And then we'll convert that MEL spectrogram. It can be either refined or not refined. It's an optional step using a conditional flow matching decoder. So this was our training architecture. For inference, we have the text to phoneme, phoneme to MEL, and then MEL is converted to audio with the help of hi-fi GAN. For evaluation strategies, we are using these 5 metrics: word error rate, character error rate, real-time factor, mean opinion score, and speaker similarity score. So these are our outcomes. So we can see it's for speaker similarity, we used WaveLM SV embeddings and computed the cosine similarity. For RTF, we are getting good scores for the first 7. The last 4, the RTF is a bit high. And similar for the MOS code as well. However, it works fine with the speaker embeddings. And so here are some sample outputs if you want to listen. And so these are the main outcomes of our work. So it has reported good MOS scores for Hindi and Telugu, and it maintains good speaker similarity, and also it is having a less real-time factor.
Can we open the thing?
For sample audios?
Sample audios. Yeah. Can we?
It's interesting that you mentioned using articulatory features, which I haven't heard about for quite some time. So do you think that that made a difference in the ultimate output? What were your motivations for using that?
Because we have the, so many of the languages are using the same script, Devanagari script. So converting them, instead of treating them as different tokens, if we can convert all of them into just how it is pronounced, if it's a vowel or a consonant, voiced or unvoiced. So it would lead us to a common space instead of having multiple tokens, or even if the same character being encoded multiple times for all the languages.
How did you handle the affiliates? We talked about articulating.
Yes.
It's not just voice and voice, right?
Yeah.
You also have to use the place of articulation and manner of articulation.
Right.
Manner of articulation, you're saying, okay, you'll do voiced and voiced. What about place of articulation? We talked about bilabial and things like that. Indian languages have affricates.
Right.
So that's, in fact, that's one thing which doesn't get spoken properly at all. So how did you give these articulatory? What is that 64 dimension in your?
Yeah, we can show that. We'll have, so we had a 64 list of dimensions. We can open that.
Now, does it correspond to actually articulatory?
Yes,
movement?
it corresponds to sound units like consonant, affricates, bilabial, fricatives, etc. So, sorry?
Where do you get that list from?
So it was already available in the 64 list of articulatory features. Can you open that link?
Okay, another question. The toucan, did you take a pre-trained model, or
Yes.
did you train from cold start?
No, we took a pre-trained model.
What was it pre-trained on?
So it was pre-trained on 7,000 languages, including Indian and European and many other languages. Like it was trained on 462 high resource languages, and remaining were all low resource.
So did you do, as you said, some ablation studies to check without articulatory features, how did it perform? So how did you give these articulatory features? Because this is new, right? You're giving it, or toucan already has a facility to give articulatory features?
It has the facility to give,
Oh, so
and
the
it has
64 parameters are from toucan.
Yes. Yes, ma'am. These are the ones. So for every phoneme, it has those features. So that's the last two are the place of articulation and the manner of articulation. Then we have the position of the tongue as vowel frontness, and others are voiced, unvoiced.
Is this adequate for something like Bengali, which has 3 different A's, no? Did you check it? You're a
No.
Bengali, no?
Yes.
So what you write, for example, you write one single A, but it
Right. Yeah.
does it take care of all of that? Or
Not
did you-
always.
Not always.
Not
means what do you
always.
mean? Did you try to see how to augment
So
this?
I just tested with my name. It is supposed to be pronounced as Onindita, but it said something else, Unindita. So we have O and O for the same representation, and it's not really rule based. We don't have a rule when we will say O and O, but in this case it was not
There
always.
must be a rule, no? You could have processed it and given it, no?
Yeah.
So just taking something off the desktop and not fixing it for Indian language is not a great idea, right?
Hmm.
How do you take care of real and all that?
Excuse me. I have a question. So these articulatory labels are text-based, right?
Right.
So when you have all this data set, but the thing is, sometimes pronunciation and what are phoneme, they don't match because of accents and other things, right? So ideally, wouldn't it be better to have some kind of setup that predicts this tokens, articulatory labels or tokens based on acoustic features than text itself? Because I work with like, articulated trajectories and stuff, so usually phonemes, whatever you get, are not usually what they have pronounced.
Right.
That happens a lot when you have articulatory features which are based on phonemes. So don't you think that would have benefited a model like this better than just using text-based?
Okay, so apart from only using the text-based articulatory features, we are concatenating them with the speech features and then predicting the pitch duration and energy. So,
I'm sorry, can you repeat that?
so we are using the ground truth, pitch, energy and duration to be predicted from these articulatory features for constructing the MEL spectrogram. So this is our starting point when our text is converted to these features and then passed to the transformer encoders.
But usually it's not pitch and energy, right? If you think about accents and articulatory features, it's usually position of tongue, lips and these things. So
Right.
Ideally, wouldn't you want to have like these labels predicted from, let's say, if you have this reference audio, right? If you predict these kind of features using the reference audio, it's just an example,
Right.
use those in some kind of embedding to condition the model so that whatever the model produces, the audio, will have that kind of accent in the predicted audio.
Okay, so you're asking instead of using the E kappa TDNN for the speaker, instead of using the
In
speaker.
addition to that, you could use. That's what
Okay,
I'm saying.
yeah, we could have done that.
ఈసారి కూడా జూన్ 21
So we are playing one sample. So this is a reference audio.
తేదీన మన దేశంతో పాటు ప్రపంచం నలుమూల
So this is a reference audio, and this is a sentence.
Hello. Hi. So, yeah, you told that you took a pre-trained model and you then fine-tuned on other languages.
Yes.
So my question is, when you train the model for the first language, then you go to second language and third and fourth, so on. So does the acoustic information carried out from the first point to the last final output? If yes, then how do you tackle this issue? And if no, that how this happens?
Can I?
Okay, so the pre-trained model which we have taken, it supports almost 7,000 languages. So because it has some language embedding space, so with that, so it supports 7,000 languages. So that's why we have taken that, and on top of that, we have fine-tuned it.
And the fine tuning is not sequential, like it's not that we fine tune the pre-trained model on English and then fine tune it on Hindi. We are fine tuning the whole thing on 600 hours of 11 languages data.
So you fine-tuned separately.
No, we did not.
Then
So the single model supports all the languages. So we fine-tuned on top of that. So it's not like we are adapting any language.
You know what she's asking?
Oh, okay, okay.
Train on one and then follow with the next one.
Okay.
Then the phonemes of one language will get carried to another.
Okay.
Or did you randomize the entire input and do it?
Yes, we randomized, ma'am. So we randomized the entire input.
You put the all languages you randomized.
Yes. So I'll just play some audios. So I'll play the reference audio again. So this we have.
ఈసారి కూడా జూన్ 21వ తేదీన మన దేశంతో పాటు
So this is in Telugu reference audio, and this is the text which we try to synthesize, and this is the.
అనీమియా అనేది ఒక పరిస్థితి. ఇందులో విరుపు రక్త కణాల సంఖ్య లేదా వాటి ఆక్సిజన్ రవాణా సామర్థ్యం శరీరపు అవసరాలను తీర్చడానికి తగినంతగా ఉండదు.
So this is the synthesized audio. There are scenarios where things are failing, but yeah. These are in the reference audio is in Telugu only. For example, we have Bhojpuri and other languages as well. I'll play one Hindi.
आपको याद है 10 साल पहले इसका प्रारंभ हुआ.
So this is a reference audio.
नीलम रोज शाम को जंगल के पास जाती थी.
The previous audio that you played, no, there was a little bit of murmur at the end.
Yes, yes.
Do you know why that happens?
No, ma'am. Didn't check.
Huh?
No.
Happens mostly in Indian languages.
Okay.
Primarily because alignments are poor,
Okay.
especially for fricatives. Affricates, for example, you always have this problem. So that's something that's worthwhile looking at. You have an aligner, no? You used a CTC aligner, I think.
Yeah, we have an aligner to predict the timestamps of the
Ah.
phonemes.
So please check, go back and look at the spectrogram.
Okay.
You'll know what mistakes it's made.
Thank you.